All right, installment number 3 as we go through this practice exam. This problem asks us, first of all, to find the energy of interaction for this cluster that contains 4 atoms. The 4 atoms are charged, so there's a charge of 0.2 on this atom, a charge of minus 0.2 on this atom, and so on. And the total interaction energy is therefore the total of all charge-charge interactions. And there are 6 possible interactions here. There's this one, this one, this one, this one, this one, and then finally this long one between the 2 sort of end atoms. So what we have to do is add up all those possible contributions. And that's easier than it looks like at first because a lot of the distances are the same. The interaction energy for any one pair is U is equal to 1391, charge on one of the atoms in the pair, charge on the other atom in the pair, the dielectric constant, and the distance between the 2. And so if the distances are the same between any 2 pairs, then we just have to, multiply by however many pairs there are that are the same. So in this case, there's one pair here, another pair here, another one here, and then finally there. Those all have the same distance, right? The distance there is R equals, this distance is 4 angstroms, so R equals 4 angstroms. This formula here works when R is in angstroms, so that's easy. And Z is in electron units, which all these numbers are. 0.2 and minus 0.2 are both in electron units, and gives us an answer out in kilojoules per mole, and we use that constant in front. The dielectric constant in this case is for water, and so that's 80. So all we have to do is figure out what all the interaction distances are, and we can calculate the whole thing. There is one pair that we haven't talked about yet. That's this pair, this distance between these two atoms. That distance is obviously longer. What is that distance? Well, this is an equilateral triangle, right? So if we draw it as it normally would be drawn, if this side is 1, then this side is the square root of 3 over 2, and this side is a half, so that's this length and that length. And since there's 2 of those here, the total distance along the long diagonal there is just the square root of 3 times the length of one side, which is 4 angstroms. All right, so then altogether, our energy of interaction is going to be U is equal to 1391. Well, let me write it out. I was going to write it all out in a quick form, but let me write it all out long. 4 times 1391 times, let's see, times, this pair is 0.2 times minus 0.2 over 80 times 4. Let me be a little bit more careful. So that's that pair, plus, so that's just that pair, plus this pair, which is the same thing, so now there's 2 of them, plus this pair, which is also the same thing, so now there's 3 of them, plus this pair, which is also the same thing, so now there's 4 of those, plus this pair, which has the same distance, but notice it's between 2 different charges, so that's 1391 times 0.2 times 0.2 over 80 times 4, plus this long pair, which is between 2 charges of the same sign, 2 negative charges, just 1391 times minus 0.2 times minus 0.2 over 80 times the square root of 3 times 4. And that's our full answer. We can write that out in a little bit simpler form. It's going to be 1391 over 80 times 4 times 4 minus 4 plus 1 plus 1 over the square root of 3 times 0.2 squared. All right, that's just factoring out all the common things among all these terms, right? That 0.2 squared is common among them. The 1391 is common among them. The 80 times 4 is common among them. So I just took out all the common factors. That makes the calculation a little easier. Let's calculate that number now. That's 1391 over 80 times 4 times, this is minus 3. So minus 3 plus 1 over the square root of 3 times 0.2 squared. See if that, yeah, that worked out. So 0.4212, minus 0.4212. And that's in kilojoules per mole, so that's equal to minus 421.2 joules per mole, which I think is probably closer to the units that we're going to want. Then it says, assuming that, so that's the answer to the first part. Then it says, assuming that these are the only possible states for these atoms, find the absolute probability of observing a cluster versus atoms separated at infinity. So the probabilities we want then are going to be P in the cluster, which is going to be equal to the energy E to the minus U for the cluster over RT over Q. And Q is going to be equal to the number of states in the cluster, which is just 1, so that's E to the minus U for the cluster over RT, plus the energy for the state for everything separated to infinity. That's E to the minus, what's the energy when they're separated to infinity? It's 0, right? E to the minus 0 over RT. So that's equal to 1 plus E to the minus U for the cluster over RT. And that is equal to 1 plus E to the minus a minus 421.2. Our temperature is 300 kelvins, so RT is 2494 joules. And notice the plus and the plus here, so that's equal to 1 plus E to the 421.2 over 2494, and that is equal to 2.184. Now, there is something that should be pointed out here, and I think I will point this out also on another occasion, or at least as many occasions as I find opportunity to. And that is that notice in this particular case we have two states. We could draw a level diagram for this. But now we're saying that the upper state has the 0 of energy, right? We're saying that when the atoms are separated to infinity, the energy is 0. That's what I plugged in here, right, for the upper state. And the lower state has minus 421.2 for its energy. So we're doing something a little bit different than we did before. Always in the examples that we've done before, we took the lower state to be the 0 of energy. Here we're taking the upper state to be the 0 of energy. Does that make any difference? In the end, it doesn't make any difference. We will get the right answer no matter what we choose, which state we choose to be our 0 of energy. If we took this and reversed it, in other words, if I put the 0 of energy down here, but then made this plus 421.2, I'd get the same answer. I get the same probability. Let me be clear about that. I'll get a different value for Q, though. I could go into some more detail for why this is true, but let me just write down the answer, or the conclusion to be remembered. That is that the 0 of energy does not affect the probabilities. If you work out some examples, you'll see that that's true. Basically, you get the zero of energy dividing out on top and bottom when you take the probability here. There's a zero of energy factor here, there's another one here, and they divide out, so it doesn't make any difference where the zero of energy is. But it does affect the value of Q. So we're going to get a value of Q that's different than we would get when we choose the zero of energy down here. Well, when we choose the zero of energy up above, sorry, and choose this to be a negative value, we get a different value for this set of choices than we do for this set of choices. That's all right. So we've done it using the set of choices that we, let me actually circle that. It's kind of an important conclusion. So we get this 2.18 for the set of choices that we made, which was this one, not this one. So this one with the negative value down below and the zero up above. That's the choice we made. With that choice, we get this value of Q. We would have got a different value of Q if we'd made the other choice. So this is a perfectly correct answer for Q, but now we need to calculate P. P is equal to E to the minus the energy of the cluster over RT divided by Q. So P cluster is equal to E to the minus a minus 421.2 over 2494 divided by Q, and let's see what that is. Let's save this number. So P is equal to E to the minus 421.2 over 2494 over 2.184, and that is equal to 0.542. And just to reassure everybody, I did this calculation using the other convention, or the other way of assigning the zero of energy before, and got the same answer. So that's one practical demonstration that what I'm saying here is correct. If this matter confuses you, then I would say the safest thing to do is always choose the zero of energy to be on the lowest state, and make all the other energies equal to differences from that lower energy. I hope that's clear. All right, so that's the only answer that was required for part B here, and I guess we could, it doesn't actually ask for it, but we could calculate the probability of the cluster being separated to infinity. That probability is just 1 minus, right? It either has to be in the cluster or separated to infinity, so that would be 1 minus 0.4542, which is equal to 0.458, I think, if I did my arithmetic correctly there. All right. Problem number 6. A solid block of metal is in thermal contact with a temperature bath at 300 Kelvin. The block starts at a temperature of 350 K. By the way, we're now switching up to this point. We've been going over the actual exam 1 from 2 years ago. Now we're switching. These are new problems. They aren't really different in type or in style from the problems up above, but now these are new problems that were that I just wrote recently in order to give you more opportunity to practice. And so we're now leaving the old exam and going on with new stuff. So a solid block of metal is in thermal contact with a T bath at 300 Kelvin. It's usually a good idea to write a picture. So here's our T bath at 300 K. And it starts at 350. So it starts at a higher temperature than the bath temperature. It eventually equilibrates, of course, because it has to. So both block and bath are at 300 K. The fact that it's a bath means that the flow of energy out can't raise the temperature of the surroundings, right? So it has to end up at 300 K. The heat capacity of the block is 100 joules per Kelvin. And the first question asks, how much energy is transferred? Is energy lost or gained by the block? So there's obviously no work in this case. The block doesn't change volume. So it's all got to be heat. The heat will be equal to the heat capacity. And again, it doesn't say whether the heat capacity is a CV or a CP, but we're assuming negligible thermal expansion when the temperature changes, so it doesn't matter. So C delta T, the delta T is minus 50, right? And this C is 100, so 100 joules per K times minus 50, the temperature went down by 50 degrees, and so that's minus 5,000 joules. That's easy enough. The energy is obviously lost by the block, as you can see by the minus sign, and is also obvious, right? If the block had the higher temperature, then it has to have lost energy to the surroundings. Is the process reversible or irreversible? Well, the easiest test for whether something's reversible or irreversible is usually to look at all the thermodynamic forces that are involved. If the thermodynamic forces are always balanced at all points during the process, then it's reversible. If they're not balanced at any point during the process, or if any one force is unbalanced at any point during the process, then it's irreversible. In this case, the force in question is the temperature, right? The temperature of the system is different, is higher than the temperature of the surroundings or the bath, and so the forces are unbalanced. The thermodynamic forces are unbalanced, and so this is irreversible. And it's irreversible because of unbalanced forces, unbalanced temperatures. All right. What's the entropy change for the block? Well, the way you calculate an entropy change is you assume a reversible path. In this case, we have an irreversible process. So what do? We have to pretend that we got the same initial and final states. In other words, we assume that the initial state, state 1, has a temperature of 350 K, and nothing else matters, right? The pressure and the volume don't affect anything in this case. So temperature 1 is 350 K. Our final state has temperature 2 of equal to 300 K, the bath temperature. We have to hit those same initial and final states when we're doing our entropy calculation, but we're free to choose whatever path we like. We have to choose a reversible path in order to calculate entropy because we need a reversible heat change. ds is equal to dq rev divided by t. And we're going to assume that the reversible path, therefore, is that we started at 350 K, because we have to, right? That's the initial state of our system. But that the surroundings was also at 350 K, and then slowly the surroundings changed temperature until it finally got to 300 K, and both of them are at 300 K in that case. In that kind of process, the temperatures are balanced at all points, and therefore it's a reversible process. For that kind of process, delta S is equal to the heat capacity times the logarithm of the ratio of the two temperatures, T1. And so that's equal to 100 joules per K times the log of 300 over 350, right? The final temperature is 300, the initial temperature is 350. That is equal to 100 log 300 over 350, and that is equal to minus 15.42 joules per K. All right. The calculation in this case is essentially trivial, right? It's a matter of picking out the formula that we already derived in class. But knowing that that's the correct formula is a little bit not so trivial. You have to realize what you're doing. It's dangerous to just say, well, the block is cooling, let's use this formula. In this case, that would have given you the right answer. Not in all cases, though, as we will see in the next part of the problem. The next part of the problem says, what's the entropy change for the surroundings? people might be tempted to say, well, it's the same as the entropy change, the negative of the entropy change for the system, right? Because whatever heat was lost by the system had to go out into the surroundings. So the heat changes for the surroundings must be negative of the heat changes for the system, and therefore the entropy change must also be the negative of the entropy change for the system, and that's false. It sounds good, but it's wrong. The reason it's wrong is because let's look at what's happening in the surroundings. In this case, we can't pretend that the surroundings started at 350 K. That isn't true. It started at 300 K and it ended at 300 K too. In this case, the reversible path that we choose has to start from an initial state for the surroundings that has the same temperature as the final state for the surroundings. We can choose any reversible path we like, but the simple one is obviously to choose an isothermal process for the surroundings. But it has to be an isothermal process that conserves energy, which means that whatever energy loss occurred in the system has to be the negative energy loss for the surroundings. So delta S for the surroundings has to be minus the energy loss, the heat loss for the system, divided by the isothermal single temperature that all this took place at. And we know that temperature, that energy loss, it's equal to 5,000. It's going to be plus 5,000 now, right? Because the surroundings gained heat energy. And so it's going to be 5,000 joules divided by the temperature, 300, and that is equal to 16.67 joules per K. All right, now, notice that in this case, the entropy change for the system is different than the entropy change for the surroundings. And of opposite sign too, notice. If this had been a truly reversible process, if it had not been an irreversible process, if the temperatures really had been balanced at all points, if this process that we used for the entropy change of the block really had been like we pretended it was, 350 K and then everything cooling down to 300, then we would have gotten a plus 15.42 here. If for a reversible process, the entropy change in the surroundings is the same as the entropy change, as the negative of the entropy change in the system. And remember, for a reversible process, what that means is that the total entropy change would be 0. For a reversible process, the total entropy change is 0. But this was an irreversible process, and we're seeing that the total entropy change is not 0. So now, what is the total entropy change? The delta S for the universe is the delta S for the system plus the delta S for the surroundings. That's minus 15.42 plus 16.67, and that is equal to 1.25 plus 1.25 joules per degree Kelvin. So the total entropy change of the universe in this case was not 0, and it wasn't negative. It's positive. What does that mean? It means that this should be a spontaneous process. And that's a check. That's something we should have known right from the get-go, right? Because if we look at what we said is happening, a hot block is cooling down in the presence of a tea bath. A block initially at 350 K is cooling down to 300 K. We know that should be spontaneous. Right from the get-go, we should have known that the total entropy change for both system and surroundings can't be 0, and it has to in fact be positive. A spontaneous change requires a positive entropy change. It couldn't have been negative either. And that's what we got. It isn't a great big change, but it is positive, and therefore we have now an answer that's at least consistent with the a priori things we knew before we started the problem, or if we would have known if we'd thought about it a little bit. All right, I put this problem in specifically to give us a chance to exercise these rather subtle and tricky things that occur whenever you have an irreversible process. And you're going to have an irreversible process every time you have a spontaneous process. So whenever we talk about a spontaneous process from now on for the rest of the semester, and we're going to talk a lot about them, then we know that that's an irreversible process too. There's a bunch of different tests you can use for whether something's reversible or irreversible. The simplest one usually is to look for balanced or unbalanced forces. Another one is to see if somehow you know that the delta S universal for everything, for the universe, is equal to 0. Another one is whether there's any friction that you can palpably see is present, and so on. There's a bunch of different tests. I listed them at one point. All right, that's problem number 6. Problem number 7 says, well, let me stop here. I'm doing 2 problems at a time, and I guess that's probably a good idea.